Okay, now we're going to work on a little bit of a tricky problem. I've got this function called sum, and now it's got two arguments. Sum of 0 and t is equal to t. Sum of n and t is equal to sum of n take 1 and t plus n. So this function is similar to the plus function from before, but this time it uses t as like a temporary variable to store the total computed so far. Okay? So we want to prove for all natural numbers n, for all natural numbers t, sum of nt is equal to n times n plus 1 on 2 plus t. So this can be tricky because you might get stuck on, do I have to do induction over two variables, or which variable do I induct over, or the like. So how you figure that out is you look at the function and you see which variable the function is recursing over. So here, on every function call, n is getting one smaller, and eventually it'll get down to 0. So that looks like a good choice to do induction over. So when we do induction with multiple quantifiers, when we prove the base case, we have to show that for n equal to 0, for all t, this property holds with n equals 0. So in this case, our base case will be for all t, sum 0t equals 0, 0 plus 1 on 2 plus t. I haven't named my rules, so I call this S1 and I'll call this S2. Okay, so when we prove a statement with a quantifier, we're going to say, we're going to let t be arbitrary, which means t can represent any value, and we can't make any assumptions about it. So we have to prove this conditional at working for any t. So we'll take the left-hand side, which is sum 0t, which by the definition of the function is just t, by S1, which is equal to 0 times 0 plus 1 on 2. Because 0 times anything is 0, so this whole thing is 0 plus t, by math. Okay, so left-hand side equals right-hand side. So it's proven for the base case. Now we're going to prove it for the step case. Okay, so for the step case, we will assume this formula to be true for n equal to some k. So assume true for n is equal to k. So what are we assuming? We're assuming for all t, sum kt is equal to k plus 1 on 2 plus t. Okay? And then we want to prove for n is equal to k plus 1. And again, for an arbitrary t, so we want to prove for n equals to k plus 1, and for all t, sum of k plus 1 t is equal to k plus 1, k plus 2 on 2 plus t. Okay, and this assumption here we will denote as the inductive hypothesis, or IH for short. So let's prove this. So we're going to let t be arbitrary, and t be arb for short. So we'll take the left-hand side, which is equal to sum k plus 1 t. What is this equal to? By the definition of sum, if we insert k plus 1 for n, then we get sum. This term decreases by 1, so we have k plus 1 minus 1. And then we have t plus n. In this case, n was k plus 1. So t plus k plus 1. That was by S2. And then we can cancel out the plus and minus 1, so we get sum of k, t plus k plus 1 by math. I can now apply the inductive hypothesis. So even though the inductive hypothesis doesn't have a t plus k plus 1 term here, I've assumed the inductive hypothesis for any value of t. So that means it'll work for this value of t here, namely t plus k plus 1. So I can apply the inductive hypothesis and replace this term here with k plus 1 on 2, plus the value of the second argument, t plus k plus 1. Okay? What was that by? That was by the inductive hypothesis. And now what I want to do is somehow rearrange this so it looks like the right-hand side over here. Okay? So what I can do now is I can multiply both sides by 2. I'll multiply this top and bottom by 2. So k plus 1 on 2, plus 2 lots of k plus 1 on 2, plus a value of t by math. Okay, then we can combine the terms together. So we're going to have k plus 1 plus 2 k plus 1 all on 2 plus t. And what does this become? So I've got k lots of k plus 1 here. I've got 2 lots of k plus 1 here. Therefore I can factor out the k plus 1 and get k plus 2. K plus 1 on 2. So k lots of k plus 1, 2 lots of k plus 1, therefore k plus 2 lots of k plus 1 in total, plus t. And fancy that, that's equal to the right hand side. So he proves it for the base case, he proves it for the step case, therefore by induction we have 4 values n, 4 values t, sum n t is equal to n plus 1 on 2 plus t. There we go.